Good morning, everyone. Hello. I'm glad you're here to join us in this Earth Engine Reducers session. My name is Allan Kiplagat. I'm a software engineer on the Google Earth Engine team. And Nick Clinton, over here, is a developer advocate on the Google Earth Outreach team. So I'm new to the fairly new to the Google Earth Engine team, and Nick is an expert. So I'll be going through the initial portion of this presentation, and Nick might jump in and add some context that he has, and I'm looking forward to this. I'm learning a lot as well, and I hope you take away something useful here today. And if you have any question, just raise up your hand. We might get to it, but we'll try to move quickly and so we can have some time at the end for other questions as well. All right, let's go. All right. I want to get this presentation on there, and it's not on there yet. It's coming. All right, as the presentation's coming up, here's the link to get to the slides.
G4G underscore reducers underscore 2022. And that should get you to our slide deck.
And Peter back there also has a link. So we want you to see the slides because they have links to Earth Engine scripts that have some examples that are very useful. So goo.gle/G4G underscore reducers underscore 2022. Could I get a thumbs up if that's opening for you? All right, many folks have it. Excellent. All right, great. Okay. Yeah, we'll just start going with this, and I'll mention which slide we're on, and you can just look at it on your screen. And if you're following along later on in this video, you'll also have the link, so I hope you'll be able to access the slide as well. All right, Earth Engine Reducers. Now, let's go to the next slide, which at the very top says, reducers combine a bunch of values. So reducers are the way to aggregate data over time, space, bands, arrays, and other data structures in Earth Engine. The EE.reducer class specifies how data is aggregated. So on the left of that slide, you'll see various reducers you can use. And on the right, you'll see how you can do the reduction. So for example, on the left, you'll see image.reduce. So we're doing a reduction over an image, and we can combine that with a sum reducer. So we'll be doing summing as our statistic.
Yay.
Oh, yay. Awesome. Thank you, tech crew. All right. So you don't need to absorb everything in this slide. The point is you can do many types of reductions by combining things on the left and things on the right. And we have a lot of documentation that goes into detail about this. All right. So to reduce an image, use image.reduce. So this applies a reducer to all of the bands of an image. The reducer will be called at each pixel to reduce the stack of band values. And the output image will have one band for each reducer output. So in this example here, we have an image with multiple bands, and we're using a max reducer here. So over each pixel, we'll take the maximum of each band. So we'll have an output will be a single band that has been applied to all the bands to all the pixel values to a single pixel across all the bands. So we collapse that image into a single band. To reduce an image collection, use image collection dot reduce. This reduces the collection of images to an individual image, and the outputs computed pixel-wise and band-wise. So let's take an example of needing to take the median over a time series of images represented by an image collection. Each pixel in the output is composed of the median value of all the pixels in the collection at that location for each band. So this is the code snippet that you'd use. And so on the right, we have a collection of images, and we're collapsing all those images into a single image, and we're selecting, if we have, let's say, band B1 in each of those images, we'll, at every single pixel of that band, we'll take the median, and that will give us the resulting value for that band in the single image of the result. So think we'll have multiple images, multiple bands. We're collapsing those images into a single image that has multiple bands, and each of those bands at a single location tells you the median of all the pixels we saw for that band across all images. Now, there's a 2 over here at the very end. And 2 here is, this is a parallel scale parameter. So you're not expected to know this beforehand. Documentation, if you go to the documentation page, it tells you about this parameter. This is a scaling factor used to limit memory use. So if we use by default, it's 1, I believe. Using a larger parallel scale value may enable computations that run out of memory to not run out of memory with the default value. So by default, you don't need to set it, and then if you run out of memory, try bumping up that value. All right, so let's look at an example here where we want to compute the greenest pixel, the maximum NDVI composite. So if you click, there's a code link on this slide for you. If you just click on it, you'll find the entire script there. So what that script does, can I get a thumbs up if the script loads for you? Okay, awesome. So what the script does is, at the very top, if you attended the previous Intro to Earth Engine course, we saw how to import collections. So you'll see at the very top, we load a Landsat 8 image collection, and then we do some processing on that. We select 20 images from 2020 using filter date, and then we apply a mask function. You don't need to look at that mask function in much detail, but it does some pre-processing for us. It gets rid of cloudy pixels and does some scaling on the bands, and then the key thing is it computes and inserts an NDVI band there. And then, so let me just load that script here so we can look at the most interesting part. Okay, and then I will. Okay. All right, this is the most interesting part of this script. Okay, so we have a bunch of images in an image collection. We use a map function to do something to each of the images in that collection. Then this function, it does some cleanup for each image, gets rid of cloudy pixels and does some other normalization for us. And then the key part is that it adds a band. So that line right there, it computes the NDVI. So it says for this image, use those 2 bands, compute the normalized difference, and insert that band as a new band in that image. All right, now we're back here. And then we say select some particular bands. So from yesterday's session on intro, from yesterday's intro session, we think of image collections as just a bag of images. So we're saying in this bag of images, select particular bands that we're interested in. And the bands we're interested in are the NDVI band and these 3 bands here, the RGB bands. And then here's the key part that's applicable to our lesson today. We do the reduction on that. So we say, all right, at this point, after we've done the selection, we have an image collection that has, where each image has 4 bands that we're interested in, the NDVI and 3 other bands. And then we do reduce on that image collection. And we say, use the EE reducer max reducer. So what this does here is for each band, we'll find the maximum. So we'll operate on those 4 bands, finding them at each pixel, the maximum value for that band. So we'll end up with a single image that has 4 bands. Then for each band at each pixel location, we have the maximum value there. And then this set outputs part here is just a quirk that where we need to, if we don't set that, we lose the band names, but we set that there to preserve the band names. And then we visualize that by adding that greenness pixel onto the map. And that is so that's layer 1 here. Okay, let me go back to the presentation here.
Can I ask a quick question about some of the code in there?
Sure.
You've got the thermal bands broken out, and then is that because they're different scale that you have to handle them separately before you reassemble them? Is that what's going on there?
Are you talking about this part here?
Yeah, right there.
I believe these are recommended scaling that needs to be done. Is that the case, Nick?
Yeah, the scale and offset are different between the optical bands and the thermal bands, and that's why the thermal bands are handled separately.
Break them out and
You do have to break them,
separately, and then
yes.
Converting them from a DN to a reflectivity, right?
Well, in the case of the thermal bands, it's a surface temperature, yes, but
Still the same idea.
it is the scaling of digital numbers to a physical value on the landscape, and the scale factors are different between the optical bands and the thermal bands, and that's why they are handled separately.
All right. Thank you, Nick. Okay. Let me get back here. Okay. Oh, yes. There we go. All right. All right, some caveats. For image collection reductions, these particular reducers will not work with the image collection reduce function since they do not have a numeric output. And so we have the frequency histogram, and toList. And then these other reducers at the bottom will not work on an image collection reduce without first converting each input to a 1D array. You're not expected to know this in advance. When you're about to use each of these reducers, you should go read the documentation. So when you're in the code editor, you can see what each of these reducers requires as an input. And it will tell you about the 1D array. And there's more detailed documentation on the documentation website as well. Now, we can do image region reductions as well. And this is to get statistics of pixel values in a region of an EE image. So we do that using the image.reduce region function. So there's some interesting inputs here. So this is the code snippet to use. So the first thing is the reducer. So here we're using the mean reducer. The next thing is the geometry. In this case, we're using the Santa Cruz geometry. And if you click that code link, it will show you how we got this geometry. So how we got the geometry is we loaded the Tiger US Census Counties feature collection, and then we filtered for the Santa Cruz feature within that feature collection. And the code in the script shows you how that's done. So that Santa Cruz feature is a geometry. So a geometry is a polygon with some properties attached to it. And then in that script continues and then loads an image collection, a Landsat 8 image collection, and then selects one image that intersects with the Santa Cruz geometry. So the function you'll see in there is filter bounds. So we say, we take the image collection, we say filter bounds on this image collection, and we say, we give filter bounds the Santa Cruz geometry. So what that does is it looks at the bag of images and it gives back the images that intersects with the Santa Cruz polygon. And then we do this part where we perform the image region reduction. So we say, so now we know how we got the geometry. So we have the Santa Cruz geometry here. And then we set the scale here. Now, the scale says is how many meters wide a pixel is. And max pixels here says this is a guardrail. So if this computation, it's a guardrail to prevent us from doing a very large computation without wanting to do that. So let's say then now the number of pixels was very large. Let's say by mistake I wanted to run this not on Santa Cruz, but on the world, and I didn't know what I was doing, and I hit run, and maybe that's not what I want. So the number of pixels will exceed the default. I think the default is about 10 million pixels, I think, or I think about 10 million pixels. If that, before we run that expensive computation, we say, hey, error, are you sure you really want to do this? And then if you are really sure you want to do this, you change the value of max pixels. All right, and at the bottom here is a visualization of what's happening with an image region reduction, and that's Santa Cruz over there. Okay. All right, this is another example here. And it demonstrates the use of a larger max pixels value, so 10 to the 10 here. And also, something new here is the tile scale parameter here. This is a scaling factor, and it's used to adjust the aggregation tile size. And setting a larger tile scale uses smaller tiles that may enable computations that run out of memory with the default. So behind the scenes, what's happening here is that we run the computation. So the way part of the Earth Engine magic is slicing up a large computation to operate on pixel at the pixel level, so we can give that work to different servers to do that. So maybe, depending on what you're trying to do, that tile size, whatever computation needs to happen at that tile scale level, it might be still too large. And I believe the error, you see an error saying something like ran out of memory. So the way you can tweak this tile scale value, the default is 1, but you can try bumping up that value so that for that single pixel is split into more pixels. So the cost that you'll pay for that is there's some pre-setup that needs to be done to do that breaking. So your computation might run longer, but it's better. It's okay, depending on what you're doing, it might be okay for it to run longer, as long as you get the result you need. And the example script goes into more details there. And all right, some caveats here. These reducers will not work on reduced region without first converting the image to an array image. And like I mentioned before, you don't need to know this in advance, but the documentation tells you what the requirements are for each reducer. All right, now let's look at image regions reduction. So to get image statistics in multiple regions stored in a feature collection, you can use reduce regions. So the inputs are the collection, so you have the feature collection we're interested in. The example script does some setup. So the sample script at the bottom here, what it does is it loads a feature collection of counties in Maine, and then it loads a Landsat 8 image collection and uses filter bounds and filter date to narrow down that image collection to 2020 images that intersect with the Maine counties. And then we perform an image regions reduction using this reduce regions function here. So notice that we set the tile, this is another use of the tile scale parameter that we talked about before. Yeah, so reduce region, you have a single feature that you're reducing over, and then regions, you can pass in multiple features. Yes?
So the dot geometry, in the previous case, reduce region. So what does the dot geometry does? Why we need dot geometry?
The question is, why do we need, let's go back here. This, when you're setting the geometry here, we say region dot geometry. So in this script, region is a feature, and that feature is composed of a geometry and some additional items. So we're saying dot geometry to say, for this feature, just give me the geometry part of it and pass it along into reduce region.
I have another question. On the tile scale, in simple terms, does that mean what you're doing is increasing the parallelization of the processing by just breaking it into 4 chunks instead of 1?
Yes.
Okay.
Yes.
Let me dive in there. The default tile size is 256 by 256. If that doesn't fit into memory on a single machine, you'll get a user memory limit exceeded. You can chop those 256 by 256 tiles into pieces. So tile scale 2 gives you 4 pieces, tile scale 4 gives you 16 pieces, and so forth. You can keep doing that until the tile is small enough to fit into memory of a single machine, which will allow your computation to succeed. That's fine.
All right, we have a pop quiz. What should we do if reduce regions times out? I heard a whisper of the answer. Aha, yes, you can change the scale.
Yeah, let me just give you the answer here. You should adjust the tile scale if you get a memory error. If you get a timeout, you should export the collection. So reduce regions takes as input a feature collection and outputs a feature collection. If the feature collection you're trying to output times out, export it.
But then you're kind of like limited in building charts, no? Because if you're collecting from the result from this region of the chart.
Well, you can still make a chart from the same feature collection. You just have to import it after you export it.
All right. You can do image neighborhood reductions as well, also referred to as convolution. And we do that using the reduce neighborhood function. So in this case, the reduction will occur in a sliding window over the input image. So in the top right there. And then the window size and shape is specified by the ee.kernel. So in this code snippet here, we're computing the standard deviation, and the kernel is a circle of pixel size 7. So at each pixel, we look at the neighboring pixel and compute the standard deviation as that point there. And this script it's a nice example of this. So if you click on it, what the script is doing is it creates a rectangle geometry encompassing a redwood forest in Northern California. And then it loads a National Agriculture Image Program image collection and selects 2012 images intersecting with that forest. And then runs an interesting function. I think it calls .mosaic on that and creates a mosaic for you. And
Let me just dive in here for a second. The important thing in this is reduce neighborhood. This is a convolution for those familiar with image processing. Reduce region performs a convolution which may or may not be linear. You can use a linear sum or average or something in there, or you can use a nonlinear reducer such as median or mode or something like that. And the kernel size, the 7 is actually pixel radius. So if you want to have a small, adjust that to change the size of your kernel. Sorry, go ahead.
Yes, so that particular script it's a nice way to show the texture of an area after what's happening at the bottom left over here. There's some logging that has happened in there, and it shows up more in the resulting image because we've been looking at the difference between each pixel with its neighboring pixel. So on the top right, there's no logging, so it's very even, very smooth. And then bottom left, it's very strongly textured there. And then we can reduce properties of features in a feature collection as well. And we use the feature collection.reduce columns function. And so in this sample script, we're loading US Census data for the Benton County in Oregon. And we select features that have 2 properties we care about: population and housing units. And after that, this code snippet comes into action where we call reduce columns, and this selectors portion of it says, I'm interested in 2 columns. So in the script, the P1 and P2 are the names of the population and housing units properties. And then a key part here is we pass the reducer as sum, but then we have this part that says repeat 2. So unlike image collection reduce, where reducers are automatically repeated for each band, reducers on a feature collection must explicitly be repeated using repeat 2. So this is a quirky thing that you need to do. So you specify I want to repeat this reducer n times for my n inputs. All right.
All right, let me take over from here. Thank you very much, Allan, for getting them warmed up for me. How many folks are checking email? None. Okay, good. All right. So we talked about reducing images, reducing image collections, reducing tables. What else did we talk about? I think that's it. You can also reduce lists, arrays, all the stuff that you saw in the first set of slides there. Couple just review points that are important to note here. Scale is always in meters. Unless you explicitly specify that it's in the units of some other projection, it's always in meters. Tile scale is not meters. Tile scale is the size of the tiles that are being used for computation in the background. So don't confuse scale with tile scale. Scale is in meters, tile scale is in, the factor by which you want to chop up your input tiles. Okay. Reduced to vectors is the standard way to do a raster to vector conversion in Earth Engine. The important thing to note here is just reduced to vectors. An image comes in and features come out. That's what those black lines are over there. Note, first of all, you should always specify a smallish region in which you want to do this. Second of all, don't use a tiny scale. So, pop quiz, what are the units of scale? Oh, you guys are so good. Okay. Do not turn that thing down to 1. Sadness will ensue. See this best practices doc linked at the bottom for, why not to use a tiny scale with a gigantic region. You'll have, extremely complex polygons, and Earth Engine will not be happy. Okay, vector to raster conversion. This is called reduced to image, and this one's pretty safe. You can take fairly complex input rasters input vectors and make an output raster out of them. So one thing that you sometimes want to do is get a multi-band image from multiple properties of the input feature collection. I don't think I put that into this example, but you would specify more than one property here, and then you would have a dot for each on the reducer. So this is kind of analogous to repeat. You just want it to do a separate reduction for each of the inputs that you're specifying in this inputs list. Okay. Grouped reductions. It's handy to sort of have a separate reduction for each group of the input. And here's how you do that. First of all, because this is a table reduction, you have to repeat the reducer for each of the properties that you want to reduce. So the inputs here are these 3 things, and you're repeating the reducer for the first two, and then you're grouping on the input indexed by 2. This is 0, this is 1, this is 2. So what's happening here is you're getting a sum reducer for the pop 10 input, for the housing 10 input, and then you are grouping it by state. And so that's how you do a grouped reduction on a table. Questions? Okay, group reductions on images. Also known as zonal statistics, or at least it used to be. I don't know, it's been a while since I've used other softwares, but used to be called zonal statistics. This is how you do that in Earth Engine. Same idea. Here we're reducing an image, specifically reduce region of an image. So we're choosing an input geometry, and we're saying, what are we saying? We want the mean of something. I think this is, oh, okay, I remember. This is the mean of nighttime lights change by land cover. So I thought that was kind of interesting, which land cover is experiencing the most development, that kind of thing. That was the motivation of this little example here. So what you want to do is you want to reduce that input image, which again is nighttime lights difference, but there's another band inside that image. It's land cover. And so we set the group field to 1. The input indexed by 1, the nighttime lights difference is 0, the land cover is 1, and that's it. The output of this thing is a little bit weird, though. It's this dictionary structure. So when you do a reduce region, you get a dictionary. When you do a reduce regions, you get a feature collection. Here you get this this object which contains a list of all the different each group. Each group gets an item in the list, and it tells you the code or the value. It's just the land cover index here, and then it tells you what the output of the reducer here is, which in this case is sum. And it's interesting to examine which land covers have experienced the most development. So that's that example. Questions?
I think I know the answer to this, but that's by class, not by non-contiguous cluster of class, right? So if you're, does that make sense?
Yeah, so the input to this thing is pixels. And each pixel has got one value for land cover and one value for nighttime lights change, and it's going to add all that stuff up.
This doesn't care if they're non-contiguous.
Doesn't know anything about spatial context here. Okay, weighted reductions. This example will warp your mind. And oh, is this the one that warps your mind? No, actually, it's coming up soon. Okay, how does prepare to take the blue pill right now? Okay, that's what's going to happen. All right, let's go down the rabbit hole here. What's the difference? In fact, I thought I had an image here. I'm not sure what happened to it. What's the difference? Reduce region two different ways. One with a regular old reducer, another with an unweighted reducer.
Is that going to count the number of?
Yeah, I don't know what happened to my image, but click the link to see more. How does this work? The input weights to the reducer are set by the mask of the image. So when you have a geometry that spans pixels, like through the middle of the pixels, what's going to happen is it will compute the weight of those pixels based on the fraction of the pixel area that's in the region you want to reduce. That's the normal, that's the weighted reducer. Let's say you don't want that to happen. You would like to include every pixel on the edge, based on some criterion. That is an unweighted reducer. The weight is just 0 or 1. And it's 1 if the centroid of the pixel is in the region, and it's 0 otherwise. So as you'll see in this example, you will get a different answer by unweighting the reducer. And we'll see some more of that stuff later. But
So if your geometry has contiguous features, will the edge pixels be counted twice?
if the geometry,
If it was in the weighted one?
In the unweighted?
you'd have to have a really crazy geometry to get that to happen. It would have to have like a loop-de-loop or something, and then you would get an error. Earth Engine would not like that geometry.
But no, right? Because it's zeros and ones.
Earth Engine would not like the geometry if it's got a loop in it. Yes?
Can you give an example when one might want to use this unweighted variation? Like a case study?
Yes. That example is coming. Stay tuned. Later in this same deck here. Okay, split weights. More on weights. I think this is actually the example that warps your mind, which is why I didn't put the code here. This also happens to have the unweighted example in it. Why you would want to do this. We'll get into it more later when we get to reduce resolution. But to suffice it to say that if you don't want your weights to come from the mask, if you want to provide your own weights, then you can do that. And split weights will turn a single input reducer, such as average or sum, into a two input reducer in which the second input is the weight. So if you want to do weighted reductions, you provide two inputs instead of one, where the second input is the weight. Questions? Okay. Most reducers are weighted. As I mentioned previously, if you don't say anything, then the reducer is going to use the pixel mask as the weight. And you should always keep that in mind when you have these partially masked pixels. You know, you want to be careful about that, just to make sure that you're actually getting the result that you want. Pay attention to the mask of those pixels. The next part here is just what I just explained. The weight of the pixels is set by their intersection with the region, unless you choose unweighted, in which case the pixel is in if the centroid is in and out otherwise. Okay, this is my favorite one. Let's say that you want to reduce a region or reduce an image or an image collection or whatever it is. You're going to reduce something. But you want, say, the mean and standard deviation. You know, that's a real common thing to do. You want to compute some statistics or something or other. What is tempting to do is say image.reduce region, you know, with the mean reducer, and then image.reduce region again with the standard deviation reducer, and then, you know, do something with those two numbers. Don't do that. Instead, combine the reducers. And specifically, combine the reducers with shared inputs true. I'm not sure why you would ever want this without shared inputs to be true. So just set that to be true. And what that will do is that will result in a single pass over the data for both the reducers at the same time. So if you have two separate reductions, it's going to go through all the data once, compute the mean, and then go through it again and compute the standard deviation. If you first combine the reducers with shared inputs true, you will have a single pass through the data, which will be much faster and more efficient.
And in the end, you have two outputs in your dictionary.
Yes, you'll have as many outputs as you have inputs or reducers, and I think what it does is it appends a little underscore and then the name of the reducer. So you'll have underscore mean, you know, band 1 underscore mean and band 1 underscore STD DEV, you know, for standard deviation, that kind of thing. Other questions? Yes. Sorry? Yeah, the question is, can you keep on combining? And the answer is yes. You know, this thing is actually a single reducer, and you can say dot combine on that thing too to add more. I called it reducers. I should have called it combined reducer or something like that.
Maybe you're gonna mention about that, but if I want to just bring these results to my feature collection, do I need to use set? Or maybe there's another better way to do that, like to bring this number to my feature collection?
Yeah, pop quiz. What's the output of this? A dictionary, right. So you can either set that on your feature, or if you have multiple features going in, you use reduce regions. Okay, reducers can have multiple inputs and multiple outputs. Reducers like median, min, sum, etc. are single input and single output, but some reducers have single input, multiple output, for example, percentiles. So Noel was talking about percentiles yesterday in the classification 1 class, and whoops. And you noted that instead of having a single like median output, you have a bunch of outputs, and that's useful for classification. There are also reducers with multiple inputs and multiple outputs, such as the linear regression reducer, which we'll talk about in a second. Pop quiz, fix that script. Let's see if we can go here without causing absolute chaos. Okay, what's going on here? I would like the covariance over time for this image collection, and I would like the covariance in a region for these two bands, but this is broken. Why is it broken? How do I fix it? All right, so I'll fix the first one first. This is going to be, let's see if I can not break something here. All right, I'm not going to fix this. I'm just going to tell you how. No, it's all right. I'm just going to tell you how to fix this. Map a function that converts each image to an array image. So this is just map function return image.toArray, and that's it. In the second one, you want to put right after the reduce median .toArray. What is it doing? It is turning the two-band input into a single-band length 2 vector input. So the covariance reducer expects its inputs as these vectors, and it's going to compute the covariance of the stuff in the vectors. So that's why you need to convert the image, not the image collection, you convert the image to an array image. So in this case, it goes right after the median. In the first case, you have to map a function over the collection and convert each image to an array image first. I was trying this morning. You get a memory error if you fix the first one. So pop quiz, what do you do about the memory error? Tile scale, yes, you can. So a bunch of answers here. You can increase the scale. You know, you can increase the scale in meters. Normally people want, full resolution, so they don't want to do that. So you increase tile scale. That is actually not enough here because this is a lot of data. So I had to filter date on this collection as well to just reduce the number of inputs, but that will give you a nice covariance image. Okay, done with this stuff. Questions about this before I take it away? Okay, so that's the covariance reducer. Done with that. Okay, so the answer to the quiz is called .toArray on the input images. Linear regression. So there are a couple ways to perform linear regression in Earth Engine. You can use a classifier for, in regression mode. Let's see, is that true? Do we have a linear regression classifier? I'm actually not sure about that. You can get a regression from a regression tree. So for example, you can use a cart in regression mode. This is how you do linear regression. There are actually other ways using matrices. See the examples in the code editor for details on that. The point that I would like to make here is that the inputs need to be in a specific order. Can't see this damn thing. Okay. The inputs come before the outputs. So in this case, we have a linear regression on temperature and precipitation or something. And the inputs are time and a constant. I'm doing this from memory. The outputs are precipitation and temperature. So when you do, so I have my band names here. The inputs are a constant and the predictor. So let me just note, if you're doing linear regression and you want a constant term in your regression, you need to add it yourself. So here there's an image of ones or something in there. That will give you the constant term. But we also have two response variables. We've got temperature and precipitation. So it's going to do a regression over time on each of those, where in the US is precipitation going to go up or down, or temperature going to go up or down, according to this climate projection. What you get out of this linear regression reducer is an array image. And you've got to unpack the bands from that array image. And the way that you do that is you select the coefficients. And then you would call dot array flatten with this list of lists. So specifically, what these lists are lists of the labels of the 0 axis first, and a list of the labels of the 1 axis. So here's the shape of this little array that's getting returned here. And note, on the 0 axis, you've got the constant and you've got the predictor. And on the 1 axis, you've got the coefficient of response 1, and the coefficients of response 1 and the coefficients of response 2. And you want to, Earth Engine doesn't know how to display this, doesn't know how to do, you've got this little 2x2 array in each pixel. So you're just saying, when you call array flatten on that, it just turns that into a multi-band thing, where it will say, it will append these names together, constant underscore response 1, constant underscore response 2, that kind of thing. Questions about that? Histograms.
Hey, this is a quick question for, do you have any type of filter implemented to reduce spatial autocorrelation? Do you want to perform a regression, but you have autocorrelated samples and you want to reduce or NI or something like that? Is there any type of method implemented?
You could roll your own.
Really?
Yeah. Yeah, so specifically, this is all done pixel-wise. So it doesn't know anything about your inputs, are they next to each other or not, it has no idea. So you'd have to do, if you've got a table and you want to build your linear regression from that table, yeah, you'd have to know, these points are too close together, I don't want those or something. Okay, histograms. So as Allan mentioned previously, you can't use those histograms on everything. If you do, say, a frequency histogram on an image, you're going to get an error because it doesn't know how to cram a histogram into a pixel. There are some histogram reducers that are suitable for use with images, and they will say so in the docs. I believe this is a fixed 2D histogram or something in this example. The idea is that you're kind of setting the shape of the output to an array, an array of bin centers and an array of counts. And Earth Engine knows how to put these arrays into pixels. So some of the histogram reducers will give you objects, some of them will give you arrays. You have to choose appropriately depending on whether you're reducing images or tables. This is just land surface temperature over time or something. I thought it was going to get much hotter here, but it didn't, so I don't know. Anyway, you can look around and see if you can find any places where the land surface temperature has gotten much hotter recently. Questions about histograms? Reduce connected components. So this is actually from our image segmentation example. So this is an example of object-based image analysis. You want to classify objects rather than pixels, and those objects have emergent properties like mean, standard deviation, size, shape, all that stuff is useful to the classifier. What you don't want to do here is compute these segments, do a reduce to vectors, and then try to shove the input imagery into the result of reduced to vectors. Don't do that. Instead, what you should do is compute the image of segments and then use reduce connected components, which is keeping our reduction in the raster world, but it's being applied to these blocks of contiguous pixels with the same value. Let me repeat that because this is worth repeating. Do not turn that into vectors and then use reduce regions. You will be sad. Instead, use reduced connected components when you've got an image of contiguous regions and you want to get some value in each one of those regions. Okay, we have 5 more minutes, is that right? Okay, let me see. All right, good. Last example. Yes?
For that last parameter for reducing connected components, is there actually a max, or can that just be set to
That's a fantastic question. I vaguely recall complaining and getting that raised to 512, but I'm not sure what it is.
It's not the number of actual clusters, is it?
No, this is the number of pixels that will be accumulated by the reducer in a component before it spits out an output. So if it's finding chunks with more than 256 pixels here, I think you're going to get an error. So yeah, please crank that thing as high as you want it to be cranked, and then if you get an error, file a feature request. Okay, that's true that. If you get an error and it's because the parameter doesn't go as high as you want, please do file a feature request. You know, we get lots of feature requests at these events, and it means a lot more when it comes from you folks. So if you go to our support page in the docs, you'll find the link to request those features. Reduced resolution. This one seems to bite everybody, including me. It's wacky. Okay, here's what you want to do. The way Earth Engine works is that when you perform reductions at different scales, Earth Engine will pull the inputs from the image pyramid based on the scale that you select. That is not always what you want. You might want to add up the little pixels in the big pixels of some other thing. And that's what we're trying to do here. So if you're adding up the little pixels, you're doing something different than what Earth Engine does by default, which is it takes the average. It takes the average for continuous variables, and it takes the mode, I think, for discrete variables. Maybe you don't want to do that. Maybe you want to count stuff or, you know,